This is Facility Science Podcast number 22. I am Jason Doolittle, and today I'm talking about three-phase power. And I covered some of the basic concepts of electricity and power in number 6 of this podcast. So if you want a quick refresh in the basic concepts of current and voltage and that kind of thing, you can go back and listen to that one. I also want to say right off the bat here that there are many ways that power is distributed and connected, and whatever I'm going to describe here, what in my experience is the typical or basic setup, so your actual experience may vary, and consult your local experts and so forth. So first, I think I should tell you what exactly three-phase means, and for that we need to start with alternating current. And for me, the easiest way to understand alternating current has always been in comparison to direct current. So let's start there. So if you think about a battery, you know that it has a positive terminal and a negative terminal. And by convention, the positive terminal is at a higher voltage than the negative terminal. And we say, again, by convention, that the charges flow from the positive terminal to the negative terminal. And since voltage represents the relative energy level between two places, it's a good way to think of it. So as the charged particles travel from positive to negative, they have to lose some energy. They have to expend some energy somewhere. And so what we do is we arrange the devices we want to provide power to between the positive and negative terminals of the battery, connected by some wires, so that excess energy that the charged particles have when they're traveling from that higher voltage place to the lower voltage place will be dropped off inside of our devices. And the loop from the positive terminal through the devices and back to the negative terminal is called a circuit. And I've just described to you direct current. That is the case where the current is always traveling through the circuit in the same direction. Alternating current, on the other hand, isn't always traveling in the same direction. It alternates, first traveling one direction and then the other, which you should note also means that the voltage is changing polarity or direction at the same time, because current's always going to flow in the direction of the voltage. And most of our power transmission and distribution systems use alternating current, and that's generally what is delivered to our buildings. And there are various reasons for this. Two notable ones are that in some circumstances, alternating current can travel over long distances with less energy loss than direct current, and also that most of our power generating devices generate power by spinning magnets inside coils of wire, which naturally creates alternating current. Okay, so our alternating current looks like a sine wave or a cosine, if you prefer. That means that and we'll just sort of to choose a starting point randomly. It starts at zero current, so no current flowing in either direction, and then the current starts flowing in one direction with increasing magnitude until it reaches some maximum magnitude value. Then from the maximum, it falls back down to zero, and then the current starts flowing in the other direction, gradually increasing in magnitude in that direction until it reaches the same maximum value it reached while flowing in the other direction, and then gradually falling back towards zero current. And the current just repeats this pattern over and over, 50 or 60 times per second, 50 or 60 hertz, the frequency, depending on where in the world you are, it's 50 or 60. And in trigonometry and signal analysis, there is a concept called phase shift or phase angle. And so when looking at a periodically oscillating signal, one that simply repeats the same pattern over and over, like our alternating current sine wave, there isn't really a starting or ending point of the oscillation. If it's doing the same thing over and over again, you can sort of choose any spot in time and it'll basically look the same. We can draw 2 or 3 of them on top of each other in a way that they line up exactly, no matter how long they've been running or whatever. We can also, though, draw them on top of each other so that they don't overlap. For instance, we could have one sine wave signal at 0 and starting to go upward in one direction while another is already halfway up to its maximum. Both sine waves are doing exactly the same thing, but they're doing it at slightly different times. And when we have two identical but time-shifted signals like this, we call the difference between them the phase angle or phase shift. So same basic signal shape, but when we compare two of them, they're shifted slightly in time. That's called a phase shift. So when we bring alternating current to a device, which we do very often, sometimes we bring one AC wire to the device. We call this the hot wire. But if we want any current to actually flow through our devices, we need another wire to complete the circuit. So we also commonly connect a grounded neutral, sometimes it's not grounded, but often grounded, neutral wire to complete the circuit. We call this a single phase alternating current. Other times, instead of bringing one AC wire and one neutral wire to a device, we bring 3 AC wires to the device. Each alternating current wire is carrying alternating current of the same type. so the same frequency, 50 or 60 hertz, and the same maximum current or voltage amplitude in each direction. But each of them is phase shifted a third of the way through the cycle relative to the others. This means that none of them are at zero at the same time, and none of them are at the maximum magnitude in either direction at the same time. And because of the magic of the way these current sinusoids combine with each other, the three wires can complete the circuit for each other, making the extra neutral wire unnecessary in many cases. And we call this arrangement three-phase power or three-phase alternating current. It's three-phase because we have that sinusoidal current pattern on each wire, but on each wire they're phase shifted a third of the way around relative to each other. And generally we call the three-phase wires lines. So a three-phase system has three lines. We often label these A phase, B phase, and C phase, or something similar to differentiate them. And in a three-phase system, we talk about line voltage and phase voltage. All right, so to define those terms here, line voltage is the voltage measured between any two lines. And in general, for a properly operating system, the voltage between each pair of lines is the same. So the A to B voltage is the same as the B to C voltage, is the same as the C to A voltage. And then the other term, phase voltage, is the voltage measured between each phase and neutral, if there is a neutral in the system. Often it's also the ground because the neutral is grounded. And I mentioned before that a three-phase system doesn't necessarily need a neutral conductor. However, often three-phase systems are set up with a neutral wire so that the three-phase system can be used as three separate single-phase systems. Now, in the US where I am, common voltages for three-phase systems are 208, 120. So the 208 there, that's the line voltage. That's the voltage between any two phases, 208 volts. And the 120 is the voltage between any phase and neutral. That's the phase voltage. Another very common one is 480, 277. So the line voltage from one phase to the other phase, that's 480 volts. And then the line to neutral, or the phase voltage is 277 volts, and more rarely we also have sometimes 600 and 347. You might have noticed something that seems a little weird there with the 208 120. Maybe if you've ever done any electrical work at home and you live in the US. If you use one of the lines and the neutral, you get 120 volts, but if you use two of the lines, you get 208 volts, and you might have expected 240 volts. And in residential homes in the US, it's common to have a 240-120 split phase system, which is not the same as a three-phase system. So in this arrangement, you get two lines and a neutral coming to the house. And if you use one line and a neutral, you get 120 volts. And if you use both lines, you get 240 volts. And the difference is because in the 240-120 system, the two lines are 180 degrees out of phase with each other. So they're halfway shifted. That means that when one is at the maximum voltage or current in one direction, the other is at the maximum voltage or current in the other direction. So you get the maximum possible voltage difference between the two. That's the 240. In the three-phase scenario, the two lines are only 120 degrees out of phase with each other. So only 1/3 unaligned rather than halfway unaligned. So when you measure between the two, you don't get the maximum possible 240 volts. You get something in between, which in the 120 volt case is 208 volts. So that explains the difference between the two. Another term you might hear from electricians and engineers when they're designing or connecting a three-phase system is phase rotation. And if you look at the oscillation of just one phase, it will look exactly like the others since they're all exactly the same repeating waveform. When you look at all of them at once, you can tell that they're shifted in time. And if you look at any part of each sine wave, say we look at the peaks, one of the phases will reach the peak first, then the other phase will reach the peak second, and then the third one, and then everything repeats. And in an isolated system, it doesn't usually matter which order you connect the phases, but when connecting two different systems together, it definitely does matter. The order of the phases, that's basically which one we call A and which one we call B and which one we call C, is called the phase rotation. And like I said, it's important when connecting two different electrical systems together. For example, if you're connecting, say, a backup generator to a building's power system, it's important to connect the generator so that the generator's phase rotation matches the utility phase rotation. And if you don't, many devices, particularly three-phase motors, won't function properly when you switch from one power source to the other. And this is something that generally only the engineers and the electricians actually designing and connecting power systems really need to understand, but when you hear it, you'll know what it means. And two other common terms you might hear around the topic of three-phase power are Y and delta. That's how the circuit is connected, Y connected or delta connected. All right, so if you draw a Y on your paper, got an uppercase Y, it has basically three sticks all meeting in the middle. And so each of those sticks represents one of the phases, and the middle represents the neutral. And so that's a system that's connected with 3 phases and a neutral, so that you can use each phase to neutral as a separate circuit. And then the other type, delta, if you draw there's a Greek letter delta, a capital delta, which is a triangle, you have 3 sticks, and each pair of sticks is connected at the corners. And that is a 3-phase system where you don't have a neutral. Instead, your circuit is from one phase to the other phase. There are also other kind of variations of these, but just so when you hear these terms, it's Y connected or it's delta connected. The basic idea is that the Y connected means that you have 3 phases and a neutral, and all the phases have the same voltage relative to neutral. And the delta is a 3-phase system connected without a neutral, basically. I mean, it's maybe a little more complicated than that, but that's the basic idea. And again, this is the kind of thing that the electricians and the engineers really need to understand, but sometimes it's helpful to know what they're talking about when they say it. Okay, so that kind of covers what 3-phase means, and all of that's great, but why do we do such a strange thing? Why do we have 3 instead of 1 or some other number? So if we distribute single phase alternating current, we need 2 wires, 1 line and 1 neutral, and then we need the neutral to complete the circuit. And the power is fed from the 1 line, meaning that that wire is connected to the output of the generator, while no power is fed on the neutral wire. We have to provide the neutral wire just to complete the circuit. So let's say we're using 2 wires to deliver 1 unit of power, whatever that is, hypothetical 1 unit of power with 2 wires. If instead we distribute 3-phase, we use 3 wires, 1 for each line, at the same voltage that our single phase was being distributed at. Power is delivered on all 3 lines, meaning all 3 are connected to the output of the generator, but 120 degrees out of phase as the generator is rotating. And each line uses the other 2 to complete the circuit. So let's say we're using 3 wires to deliver 3 units of power, right? We get the same voltage, so the same amount of power for each line that we had with the single phase situation, but no neutral, so 3 units of power for 3 wires. So in the 3-phase case, we're actually delivering 3 times the power of the single phase case and only using 1.5 times as many wires. So from the standpoint of distribution, it's more efficient in terms of how much conductor material we use to deliver a certain amount of power. And so why 3 and not 2 or some number more than 3? And any number would technically work, but 3 was chosen for practical reasons. More than 3 would be sort of increasingly more efficient purely from the perspective of the power delivered per conductor material. But the more you add, the more you complicate the infrastructure. So the more wires you have, the more space on the distribution poles you need. For a high voltage distribution line, you need a certain amount of space in between the wires so they don't get arcing because of the high voltage. So for every wire you add to that distribution system, you're gonna have to get that much more separation on the poles or whatever. Also, at any place you have to make a connection, each wire adds another terminal. Right, you need more circuit breakers, you need more fuses, you need more bus bars. So the more phases you add, the more complex your infrastructure gets. And so 3-phase was basically decided as a good compromise between getting efficiency and not making the infrastructure too complex. And another reason is that generating 3-phase power is just as easy as generating single phase, and it's almost actually easier. The way a generator basically works, most of our electric generators, is that you're rotating a magnet basically, or multiple magnets inside coils of wire. And when you move the magnets inside the coils, you're basically creating a fluctuating magnetic field, which causes current to flow in the coils of wire. And then your generator output is the wire at the end of the coil. And then we spin the magnets by rotating a shaft. We attach it to a wind turbine or a water turbine or boil water and push steam across pedal the bicycle, whatever we have to do to get that thing spinning. So the magnet spins in the coils and creates current in the coils. And a rotary generator that can generate a single phase AC can just as easily generate 3-phase AC. Instead of having 1 coil, you have 3 coils, 3 magnets, and you spin the magnets in the coils and then you generate 3 basically with the same device. And in some cases, this is actually better for the equipment because you can get a smoother spinning of that shaft, because when you induce current in the coils, that's basically creating a magnet, which causes some pushback on the shaft. And so the more poles you put around that circle, the smoother your rotation gets. I don't really want this to be a how generators work thing, so I'm going to leave that there and get into how do we use three-phase power. So for many buildings, especially larger buildings, the electricity supplied to the building by the electric utility is three-phase, and that's for the purposes of efficiently delivering large amounts of power. And often we use the three phases separately, right? We use the three phases plus a neutral as three separate single-phase systems. That's the Y-connected system. And we do this because many, if not most of our electrically powered devices are not three-phase devices. They're single-phase devices in that they only want one line voltage or mains voltage, AC wire, and a neutral wire. And this is things like our desk lamps and computers and coffee makers and all the basic stuff you have in your home or office that you just plug into a wall. And this is totally fine in a three-phase electrical system, although it is important to attempt to balance the load of the three phases, meaning that ideally we want to distribute the three phases among our single-phase devices so that we use approximately the same amount of power from each phase. I said before that the three-phase wires act to complete the circuit for each other. That's the circuit with the generator at the utility. So if we don't balance the three phases, we get current somewhere where we don't maybe want current, or an amount of current somewhere where we don't want it. Generally, it's too much current in the neutral. And the details of this I'll call outside the scope of this podcast. You might say that if you don't balance the phases, they will balance themselves, probably not with the results that we want. Now, sometimes we use two of the three phases to get more power per amp. So in the US, we commonly have a line voltage of 120 volts, which gives us 208 volts. I talked about that before when we use two of the phases. And we typically use the 208 volts for higher power devices. This is things like small air conditioners or large copiers, certain type of motors. And if you think about the things that might be in your house, again, if you live in the US, that use the 240 volts, it's the same basic kind of things, your water heaters, the dryer, that sort of thing. And then some loads, some devices are three-phase devices. And in some of those cases, we use three-phase just because it's available and we can deliver more power with less conductor material than with single-phase, or maybe deliver the same amount of power with less current, or whatever variation of that concept applies to the situation. And a good example of something like this would be an industrial heater. The function of an electric heater isn't necessarily improved by the application of three-phase power, but in buildings where it's available, we can gain the benefit of the higher transmission efficiency and also potentially some improved life or maintainability by using three phases for a device like this. And then, of course, there are some devices that are particularly suited to three-phase power. And the big one here is the AC induction motor. And the AC induction motor basically makes the world turn. Anywhere you see in a building where something's moving, and that could be physical objects are moving, conveyor belts, machine tools, or things like that, or even air or water. Anytime you see something's moving, there's probably an AC induction motor behind that somewhere. Even things that aren't necessarily spinning in a circle, they're moving in a line or back and forth, probably an AC induction motor causing that motion. And just like I don't really want this to be about how generators work, I don't really want this to be about how induction motors work either, but basically an induction motor works exactly like a generator, but instead of spinning the magnets inside, we're applying current, alternating current to the coils. The coils then cause the magnets inside to move, and their magnets are attached to the spinning shaft of the motor, and the changing magnetic fields caused by the alternating current cause the shaft of the motor to spin. And the thing about a single phase AC induction motor is that if you only have one phase, the motor won't start. Just because if you think about what you're doing is you're causing a magnet to just keep flipping over north, south, north, south, north, south. And what'll happen is that your magnet inside won't be able to get anywhere. It'll just keep kind of moving a little bit and then going back, moving a little bit and going back, and your motor won't start. And so what we do in the case of a single phase induction motor is we use a capacitor circuit, a starting circuit. And we use the capacitor, and the capacitor is a device that tries to preserve the current flowing. And so what we can do is when we have the current going in one direction, it charges the capacitor. And when it starts falling back down, the capacitor releases its charge into a different coil, which creates sort of a second phase, which can get the motor starting. We call that a start capacitor. And that works. But it's a more complex circuit. We have to also deal with the capacitor. Capacitors they're fairly reliable, but they're much more fragile than an induction motor. So generally in the life of a motor, you end up having to replace the capacitor possibly multiple times. And so it's a maintenance issue as well. There's another thing about a single phase motor or a single phase current in general is that at some point in the current cycle, there's zero current, right? In order to change directions from one to the other, it has to at some point pass through zero, so there's no current flowing, which means there's no power being delivered. And what this means is that motor is going to periodically coast, and if there's a heavy load on that motor, it's going to slow down a little bit, and then the current's going to start going in the other direction, give the motor some more power, and then it'll speed back up again. And so motor running on a single phase is not going to run very smoothly. And in certain cases, that's kind of okay. It doesn't matter that much. In some cases, it causes problems. It causes vibration in the system or whatever. And so I talked about a start capacitor before. We might add a circuit with another capacitor. We call that a run capacitor to try to smooth out the power delivery to the motor. But again, we have to deal with that capacitor circuit. So enter three-phase power here into the AC induction motor. So if we have 3 sets of coils and 3 sets of magnets inside that motor and we connect our three-phase power to it, now we have a situation where we don't need the start capacitor, because when one phase is creating the magnetic field to spin the motor a little bit and it starts to drop off, the second phase picks up and moves it a little more. And then the third phase picks it up and moves it a little more. And so we get going. And then the other thing is that at no point in the three-phase cycle do we have zero power being delivered to that motor, because there is no point where all 3 phases are passing through zero current at the same time. And so we get a much, much smoother conversion of electrical power to, spinny power to motion with a 3-phase motor than we get with a single-phase motor. A good way, I think, to think about this is to use kind of a bicycle analogy. So if you think about riding a bicycle while you're pedaling, at some point, your one foot is at the bottom and your other foot is at the top, and so you're not moving. You're stopped, so you can change direction. And the cyclists are probably going to tell me, actually, you can move your feet in a circle and you never stop. I get it. Just help me out here. I'm trying to make an analogy. So if instead you had somehow 3 legs and 3 pedals on the bike, and instead of the pedals being sort of opposite from each other, they were spaced a third of the way around, you'd be able to pedal with your 3 feet on your 3 pedals to the point where you would always be pushing with 1 foot, and you'd never have a point where neither of your feet are pushing because you're trying to change direction. So that's maybe it might be helpful to you to understand sort of the difference between single phase in a motor and 3-phase. 3-phase, you got 3 pedals going, so at all times there's somebody pushing. That's where 3-phase really shines, I think. And like I said, the AC induction motor moves everything in our buildings, and AC induction motors really like 3-phase power. And so I think that's about all I have to say about 3-phase power for now. If you have any questions or comments about this topic or suggestions for topics you'd like to hear about in the future, you can email me at podcast@facilityscience.com, or you can reach me at facilityscience on Twitter. You can find my notes for this topic at facilityscience.com, and this is number 22. If you like this podcast and you'd like to help me keep making it, head over to facilityscience.com/support and see if any of the support options there appeal to you. I hope you find this useful, and thanks for listening.